So we're still working in section 11.7, and what we're going to look at now is what causes our projectile motion problems to become three-dimensional. In these cases, in addition to having that horizontal and vertical component, so your object's being thrown both up and out, forward, we're also going to have some kind of a sideways component. To solve problems like this, it's usually best to go back and begin with our acceleration equation again, and then use integration to work our way up to velocity and position. We can no longer use those standard R of t formula that we had derived last time because we're no longer in a situation where the only force is the force of gravity, right? So let's take a look at example 6. We have a golf ball that's hit due east. Initial velocity in meters per second is given by the equation, or excuse me, by the vector 50, 0, 30. Then we also have a horizontal crosswind that's blowing south and producing an acceleration of 0.8 meters per second squared. All right? So, again, our position equation here, the one that we were using last time, assumed the absence of any forces other than gravity. I can only use this when I have nothing but gravity acting on my object. That's not the case here. In addition to gravity acting on this golf ball, we also have this crosswind. So we're no longer in a situation where we can use the R of t that we've already developed. Instead, let's think about what's going on here. I've got a three-dimensional situation. So again, we'll consider our positive y-axis north, south, east, and west. And then we've got our up direction in the z-axis. So the initial velocity was in the x and z directions. They tried to hit this ball due east, right? So our initial velocity vector is in the xz plane. Now the horizontal crosswind is going to blow slightly south, so in actual fact I would expect that my trajectory wouldn't just go forward and land on that x-axis due east, but would end up getting blown slightly south of east by the time it lands. All right. Let's begin with the acceleration vector. We were told that the acceleration is due south at 0.8 meters per square second. So that would be 0 in the x direction. It's going to go along the negative y-axis, so negative 0.8 on the y-axis. And then we have our usual gravity in the z direction. Since we're in metric here, we're going to go with a negative 9.8 meters per second squared for g. So this is my wind, and this is my gravity acceleration, gravitational acceleration. And they're both in there in my acceleration vector. All right, in order to get to velocity from acceleration, we have to integrate. Got an extra decimal place in there. Let's get rid of that extra decimal point. All right, and we'll integrate. Our velocity function then, when I integrate with respect to t, is the integral of 0 is still 0. I'll get a negative 0.8 t for the y component and a negative 9.8 t for the z component, plus my constant of integration. Now I do have an initial velocity condition. I was told that the initial velocity is 50, 0, 30. So I know that v of 0 has to be 50, 0, 30. So I know I'll get 50, 0, 30 when I plug t equals 0 in here. And of course, this entire vector becomes 0. So the constant is just 50, 0, 30. Let's go back and rewrite the whole velocity equation then. Plugging in 50, 0, 30 for c. So my x component will be 0 plus 50, or 50. And the y component is going to be negative 0.8t plus 0. And the z component, negative 9.8t plus 30. All right, I have to integrate again to get my position function, r. So we'll integrate this velocity. And that's going to give me 50t. Let's see, that'll give me a t squared over 2, so I'll end up with a negative 0.4 t squared. And here a negative 4.9 t squared plus 30t plus, again, a constant of integration. Now in this case, they didn't exactly give me the initial position, but again, since this is a golf ball, I would assume that my initial position would be 0, 0, 0, that we've started essentially with a golf ball on the ground. We won't worry too much about the height of a tee. And so I know that r of 0 is 0, 0, 0, meaning that I have to get 0, 0, 0 when I plug in t equals 0. But notice that when I plug in t equals 0, every single one of these terms is going to become 0, 0, 0, which says that c is 0, 0, 0. And that means that my position equation is just 50t, negative 0.4t squared, and negative 4.9t squared plus 30t. All right, we can now ask the same kinds of questions we asked before. First of all, the time of flight. Time of flight would be when the ball lands on the ground. And notice that the vertical component this time is the z value. So the time of flight we're going to figure out by setting z equal to 0. And of course, t equals 0, that's actually the beginning. So what have I got? 30 divided by 4.9? About 6.122 would actually be the time of flight for this golf ball. And then finally, where will the ball land? So I'm really trying to figure out what that position is right there when the ball lands. And to figure that out, we'll just plug our time of flight back into our position equation, r. And I'm just going to kind of do this as we go. We'd have 50 times 6.122 is 306.1. Negative 0.4 times that 6.122 squared is about negative 14.99. I'm just going to call it negative 15. Round to one decimal place. And then finally, plugging 6.122 in here. I know that should give me 0. This just sort of serves as a double check. and I get 0.013 is actually what my calculator gives me. That's just round off error, right? That 6.122 was already a rounded off value. So I'm comfortable enough to call that 0. It is to 1 decimal place anyway. And it should be. The ball lands when z equals 0. So when you think about the picture we drew right up here, indeed, we mostly went in the x direction, 306.1 meters. That was a long golf shot. And then we're just slightly to the south by 15 meters. So that's what the wind did to us. It caused us to blow off course by about 15 meters. Probably a bit of a superhuman golf shot there. Sorry, I probably should have made that a little bit more realistic in terms of my numbers. Would have been better in feet than meters, but you get the idea. All right. Let's take a look at one more problem like that. We're going to go to baseball here. And by the way, some of the things that we do here may help you out a little bit with that problem that I warned you would be part of your test 2. In example 7, a pitcher throws a curveball by putting spin on the ball. A simple model assumes that the spin produces sideways acceleration, that is, perpendicular to both the horizontal and vertical components. Suppose that a pitcher throws a curveball with initial velocity 130, 0, -3 from an initial position of 0, 0, 6. I'm telling us the spin produces a sideways acceleration of 8 feet per square second. And I'd like to know how far off center will the ball be when it reaches home plate. All right, so let's see here. Once again, I'm going to kind of sketch just to give myself an idea of what's happening. And let's see, we start from an initial position of 0, 0, 6. So that would be up here at 6 on the z-axis. And then it looks like the intent is to throw down the x-axis and slightly down, right? So the intent would be to throw this way, meaning home plate must be located somewhere out here on the x-axis. That's how the pitcher's trying to throw without the curve. Now, the curve produces a sideways acceleration of 8 feet per second, and it doesn't say which way, whether it goes left or right, inside or outside of home plate. So I'm just going to assume it goes in the positive y direction. All I need to know is how far off center. I don't need to know which side. So I'm going to assume that my acceleration vector is in the positive y direction, meaning that the ball will actually land slightly to the right of home plate. And my goal is to figure out how far to the right. All right, so once again, I'm going to start with an acceleration vector. There's no acceleration at all in the x direction. In the y direction, the acceleration is 8 feet per square second, and the way I've got this drawn, it's to the right. So I'll call that a positive 8. And in the z direction, I still have gravity. We are in feet, so we'll call that -32 feet per square second. So again, here's my acceleration due to the curveball. That's the acceleration due to gravity. The velocity integral of our acceleration function is going to be 0, 8t, -32t, plus a constant of acceleration. And we've seen this several times before now, so I'm going to go ahead and just talk our way through instead of writing it all out this time. At time 0, this would just become 0, 0, 0. And we know that the initial velocity vector needs to be 130, 0, -3. So really this has to be that c. So my final velocity function is going to look like 130 8t, and negative 32t minus 3. I'll get my position function by integrating the velocity function. Which is going to give me 130t, 4t squared, negative 16t squared, minus 3t, and again plus a constant of acceleration. My initial position was 0, 0, 6. And once again, I'll just point out, when I plug in t equals 0, everything goes to 0 in here. So that c value is going to have to be 0, 0, 6. So my final position equation, r of t, is 130t, 4t squared, and negative 16t squared minus 3t plus 6. All right, I'd like to know how far off center we are when the ball reaches home plate. Now, one thing I want to be careful about assuming here. The ball may not land right next to home plate. I probably drew my picture somewhat badly. In fact, hopefully the ball doesn't land right next to home plate, right? Really, it should cross home plate at a height suitable for the batter to swing at it. So I don't want to set my z value equal to 0 here. That's not going to get me what I want. Instead, I'm going to say, what is the x value going to look like when we cross home plate? Well, if you've done a little bit of research, you've probably found that the distance from the pitcher's mound to home plate, 60 feet and 6 inches, or 60.5 feet. So when we cross home plate, the x value is going to be 60.5. Well, my x value here is 130t. So that's going to give me a t value of about 0.4654. Not quite half a second. All right, I need to know how far off center I'm going to be when we have that x value. So I really want to know this y value, how far off center. And my y is 4 times t squared. And I'm getting about 0.866. So this particular curveball is going to end up crossing home plate about 0.866, just a little less than a foot off center. All right, the last part of this question says, what makes a curveball particularly difficult to hit? And the hint is, during what part of the flight does the ball actually curve the most? Justify your answer using math. So the curve occurred in the y component, right? The 4t squared, the y component is how far off center or how much that ball is curving. Let's just graph y equals 4t squared. And I only need positive values of t. That's just going to be a parabola, right? So it's going to look like something like that. And if we imagine our time, let's see, our time of flight here was 0.4654. I'm kind of making these up right now. Let's just say that's our time of flight, 0.4654 seconds. Then the y value there was 0.866. Let's take a look at how this ball curves. in roughly the first half of the flight, maybe around here. Right? That's about the first half of the pitch. It looks like the ball has curved about this much, right? Well less than half of its total curve. What happens in the second half? This is the second half of the pitch. We get all of this curve. So what makes this ball especially difficult to hit is you're not really seeing much of the curve. You can't maybe even tell that it's a curved ball for the first half of the pitch. And then the ball curves more dramatically in the second half. And that's why a curveball can be kind of a sneaky pitch. All right, we will pause here and finish up this section in our next video.